Now we would like, even though our definitions do not require any kind of calculus or derivatives or anything like that, we would like to use some of our calculus. Since we went to all the trouble of building these things, we would like to use these ideas, these calculus things and tools to talk about increasing and decreasing. And so let's suppose that f is increasing on an interval. We can do something similar for decreasing, but the increasing, once you see this, the decreasing is going to be obvious what's going to happen. So suppose f is increasing on some interval. Then if x1 is less than x2, we also get that f of x1 is less than f of x2. We're going to take each of those two inequalities and we're going to rearrange them a little bit. So the first one we're going to take and turn it into x1 minus x2 is less than 0. All I'm doing is subtracting x2 over to the left side. Then we're going to take our second inequality and do the same thing. F of x1 minus f of x2 is also less than 0. And then divide those. Then the slope between x1 and x2, again, this would not be the derivative, it would be the slope of the secant line, but that's okay. The slope between those 2 points is f of x1 minus f of x2 divided by x1 minus x2. And what can we say about those values? Well, here in orange, we've got that f of x1 minus f of x2 is less than 0, that it is a negative number. We are dividing by x1 minus x2, which we also know is a negative number. And if we divide a negative number by another negative number, what kind of value do we get? Well, we get a positive number. So the slope of an increasing function, or at least the secant line, is always positive. Since our definition of increasing and decreasing, increasing anyway, says that for any x1 or x2, no matter how far apart they are, no matter if one point is very close to the other, that this inequality is going to hold, we could maybe take a limit, say as x1 gets close to x2. And now we're talking about the derivative. If we let x1 go to x2 under a limit, we're going to get that f prime of x2 is positive. The x2 is not important, just any value of x is fine. Again, we said we can move these 2 points all over the place within our interval. So for any x in the interval from a to b, we're going to get that f prime of x is greater than 0 if f is increasing. Now that's assuming that the function is differentiable. Most of the functions that we're going to work with are, but this is going to give us a nice test for increasing functions. Similarly, if f is decreasing, we get instead that f of x1 is greater than f of x2, and we can rewrite that as f of x1 minus f of x2 is greater than 0. And when we calculate our slope, m is f of x1 minus f of x2 divided by x1 minus x2. We just argued that our numerator is a positive number. Our denominator is the same negative number that it was before. And when we divide a positive number by a negative number, we of course have to get a negative number. Apply the same idea about the derivative, take a little limit, and we get that if f is decreasing, then f prime of x is going to be negative. Now we have some nice calculus tools that will allow us to talk about increasing functions versus decreasing functions. We just have to know what the sign, S-I-G-N, of the derivative is. Notice that our inequality here says f prime of x is less than 0. Earlier we said f prime of x is greater than 0, would tell us that the function is increasing. What's there right in between greater than 0 and less than 0? It's equal to 0, and that's going to be all of those critical values that we had talked about. So, we can summarize all of that as the first derivative test for increasing or decreasing functions. We want to find the first derivative and its critical values. That is undefined values and solutions to f prime of x equals 0. We're going to divide up the number line because our definition of increasing and decreasing was always on some interval from A to B. Where do those intervals come from? We're going to divide up the number line using those critical values. We're going to pick a test value from each interval, plug that into f prime, and determine the sign, the SIGN sign. So this is going to allow us to characterize where a function is increasing versus where the function is decreasing. So let's take a little example. One of my favorite functions. Let's take f of x to be x plus 1 over x. We already know that f is not defined at 0, which means its derivative can't be defined at 0. And so we'll get critical values that come from those undefined values that we haven't seen yet. So we want to determine the intervals on which f is either increasing or decreasing. Our procedure on the previous page says we need f prime. F of x is x plus 1 over x. Another way to say that, just using the rules of algebra, not using calculus, is f of x is x plus x to the negative 1. So that f prime of x, the power rule, is going to give us 1 minus 1x to the negative 2. And the rules of algebra say that's the same as 1 minus 1 over x squared. The critical values the undefined values. Most of the time those are going to come from setting some denominator equal to 0. And so here we get x equals 0. And then solutions to f prime of x equals 0. That is 1 minus 1 over x squared equals 0. Move this 1 over x squared to the other side, and we get 1 equals 1 over x squared. Flip both sides over. We can always do the same thing to both sides of an equation, including taking the reciprocal. If we flip 1 over, we just get 1, but we'll draw it from the bottom up. And if we flip this 1 over x squared over, we just get x squared. Take the square root of both sides, and x is positive and negative 1. So this time we got 1, 2, 3 critical values for our function. Our second step we said was going to be to divide the number line up using those critical values. Those are going to give us the intervals. So we'll draw a nice number line, and then 0, 1, and negative 1 are going to split that up into 1, 2, 3, 4 intervals. Our intervals then are going to be from negative infinity to negative 1, from negative 1 to 0, from 0 to positive 1, and from 1 up to positive infinity. Because the derivative is going to be continuous as long as it is defined, this is a result that we can prove from the definition of the derivative. Whatever the sign SIGN, whatever the sign of the derivative is for, say, one value in this interval, it's going to have the same sign for every other value in this interval. And that's where this idea of picking the test values comes from. It's not going to be the case that f prime of, say, negative 2 is positive, but f prime of negative 3 is negative. That can't happen. Negative 2 and negative 3 are both in this interval, which means the derivative has to have the same sign, SIGN sign, for both of them. It doesn't mean it has to have the same value, it just has to have the same sign. So we're going to pick a test value from each one of these. Doesn't matter what we pick, as long as we pick something that's in this interval. Pick something that's convenient, something that's easy to plug into the derivative, something that's easier to plug into your calculator, something like that. So from our first interval, I'm going to pick negative 2. From the second, there are numbers between negative 1 and 0, so I'm going to pick negative 1/2. I'm going to pick positive 1/2 between 0 and 1, and I'll pick positive 2 from the interval from 1 up to positive infinity. And whatever the sign is, the SIGN sign of f prime of negative 2, it's going to be the same sign throughout this interval. Whatever the sign is when x is negative 1/2, that sign is not going to change in this portion of the number line. Every x value, we plug it into the derivative, it's going to give us the same SIGN sign. And the same for the others. F prime of negative 2, 1 minus 1 over negative 2 squared. Negative 2 squared is positive 4. 1 minus 1/4 is 3/4, which is positive. And since f prime of negative 2 is positive, f prime of x is positive for all x in that interval where negative 2 came from. So we're going to write that down up here. F prime is, it's positive when x is negative 2, means it's going to stay positive throughout this interval, and f is increasing on that interval. We're going to do the same kind of thing for each of the other three test values. F prime of negative a half, 1 minus 1 over, and I'm going to do this as a decimal, so I don't have fractions stacked on top of other fractions. 1 minus 1 over 0.5 squared is 1 minus 1 over 0.25. 1 over 0.25 is 4, and 1 minus 4 is still negative 3, and that's less than 0. That negative a half is just representative of the interval that it came from. Our derivative is going to be negative for one value of x, which means it is going to be negative for all values of x in this interval, and f is decreasing there. So we'll write that out. F prime of negative a half is less than 0. We're going to get that f prime of x is less than 0 for all x in that interval from negative 1 to 0. Same for a half. F prime of a half is 1 minus 1 over positive. Oops, this was negative a half up here. 1 minus 1 over 0.5 squared. But when we square 0.5, when we square negative 0.5, we're going to get the same thing. 1 minus 1 over 0.25 is 1 minus 4 is negative 3. That's less than 0. And since f prime of a half is negative, f prime of x will be negative. For all x in that interval from 0 to 1. And we'll include that in our little chart. F is still decreasing. And then f prime of 2, 1 minus 1 over 2 squared is 1 minus 1/4 is 3/4, still positive. And since f prime of 2 is positive, f prime of x will be positive for all x in that interval from 1 to infinity. Our derivative is positive. For one value of x, it's going to stay positive. For all other values of x, and the function f is increasing on that part of the number line. And in fact, this function is a little bit of a strange duck. I mentioned earlier is one of my favorite functions because it looks like this. The function is increasing. From negative infinity up to negative 1. And again, we are moving from the left side to the right side, so the graph is going up. Once we get to x equals negative 1, though, our function is decreasing. We cross over 0. The function's discontinuous there. It can do all sorts of crazy things. And it is still decreasing. And again, we're moving from left to right. So the little arrow that I had there at the end is not really pointing in the right direction. But decreasing, decreasing, decreasing until we get to x equals 1. And our function is increasing again. We do not consider that infinite jump at x equals 0 to be an increase, in the sense that we are defining increasing or decreasing. The function's not continuous there, and so we can't smash those two intervals, for instance, from -1 to 0 and 0 to 1. We can't combine them into a single interval because the function's not defined at 0. So I have to leave it this way. F is increasing on the interval from -infinity to -1 and from 1 to infinity. F is decreasing on the interval from -1 to 0 and 0 to 1. Again, 0 is not included in either of those, and we can't really smash those guys back together as a single interval. It's a nice little application of the derivative to determine increasing or decreasing. The next thing that we're going to do, and we're going to pick up in the next video with this same function, is talk about using this information that we just got to determine where those relative maximums and relative minimums are, because we can already kind of see here that we have a relative max and a relative min at these two points on our graph. So we'll talk about the consequences of increasing or decreasing to help us figure out whether a function has a relative maximum or minimum, how to figure out which one is which. So we'll do that in the next video. Thank you.